Now we'll look at one last example from sections 8.2 and 8.3. This example is more like what you might expect on an exam in the sense that here we could be talking about an example from 8.2 or from 8.3. We're going to have to read the prompt and then decide which section we belong in. And then we also need to be able to categorize the hypothesis test appropriately and so on. So in this one, let's start by reading the prompt and then we'll decide what section we should be applying. So here it says one common estimate for the mean top speed of leopards is 40 miles per hour. In a sample of 35 leopards, the mean top speed is 46. At the 5% significance level, does this data provide sufficient evidence to conclude that the mean top speed for all leopards differs from 40 miles per hour? And we can assume that the population standard deviation is 2.8 miles per hour. So let's talk about the assumptions that we've been applying. So it is important that the sample that we're taking of 35 leopards is a simple random sample of all leopards. So we're just picking 35 random leopards, not 35 specific leopards. So we're going to assume that. We also need either to have a normal distribution for the top speeds or a large enough sample. In this case, because the sample is larger than 30, I'll just say that we have a large enough sample. And then there's one more thing. This is the thing that distinguishes the section 8.2 hypothesis testing from section 8.3. Remember that 8.2 focuses on when sigma is known, and 8.3 focuses on when sigma is unknown. And if sigma is known, you'll be applying z values, or the standard normal distribution. And if sigma is unknown, then you have to apply the t distribution instead. But in this case, we're told that the population standard deviation is 2.8. So in this case, sigma is known. So therefore, this problem would fit into the context of section 8.2, which means we'll be using z values and the standard normal distribution. We don't have to worry about the t distribution, which is kind of nice. Okay, so let's think about what the null and alternative hypotheses should be. So the null hypothesis is going to be the one that represents equality, and what we're doing here is we're comparing the mean speed with this 40 miles per hour, which is the estimate. So the null hypothesis would just be that the mean speed is actually 40. But notice the alternative hypothesis that's stated is we want to conclude that the mean speed differs from 40. Not that it's strictly larger or strictly smaller, we just want to say that it's different from 40. So that would look like this. That's our alternative hypothesis. Now notice that in this case, because our alternative hypothesis is just that the mean differs from 40, this will be a two-tailed distribution, or I should say a two-tailed hypothesis test, because all that we're saying is that the mean is different from 40 in a significant way, and therefore we would be happy with means that live over here to the far right, but we would also be happy with means that live over here to the far left. So this will be a two-tailed hypothesis test. And we're also told the significance level in the prompt. So now we can move on to step 3, which is to compute the z-score that we're interested in. So here the sample mean that we got was 46 miles per hour. And then we subtract off the mean from the null hypothesis, which is 40. And then we should be dividing that by the standard deviation that we get in this picture. Remember that the pictures that I'm drawing are the distribution that we would expect from the sample mean if the null hypothesis is true. So if the null hypothesis is true, then we really are centered around 40, or we're supposed to be centered around 40, and our x bar values will have a standard deviation of sigma over the square root of n. So this is the shape that we would expect for our x bar results. And if we get an extreme x bar result, so one over here to the far right or to the far left, then we have reason to doubt the null hypothesis. Because the null hypothesis would expect us to get x bar results that live here in the middle. If we get x bar results that are extremely left or extremely right, then it's a little more likely that we were wrong to assert the null hypothesis and instead that the alternative hypothesis is likely. So that's essentially what we're looking for here. Now, we know the population standard deviation is 2.8, and we're taking the square root of the sample size. The sample size was 35 here. Remember that whenever you're plugging expressions like this into your calculator, it's a good idea to parenthesize the numerator and the denominator. If you're worried about that, maybe try plugging this in, but what I got is a 12.68. So that would be the z-score. What that means is that whenever we standardize, the standardized picture is always going to be centered at 0. So we recenter from 40 to 0, and what we're getting is our test statistic lives way over here at 12.68. So it's typical for z-scores to be around 1 or 2. We've seen from that table that we're normally working with z-scores that are between 0, 1, 2, 3, or they're negatives. So a z-score of 12.68 is very far away. Okay, so now let's talk about the two approaches that we can take here. This is going to be a little bit different because we are talking about a two-tailed test. So I'm going to talk you through the subtleties that show up whenever you do these two-tailed tests. So remember, with the critical value approach, we're going to decide on these critical values. That would be these markers over here and here. These will be our critical values. And these will be the values such that if x bar is more extreme than these critical values, then we would reject the null hypothesis. If instead x bar lived somewhere in the middle, like if x bar lived there, then we would accept or not reject the null hypothesis. So if x bar is pretty close to 40 like this, then we wouldn't be rejecting the null hypothesis. But if x bar lives way out here, past the critical values, then we would reject the null hypothesis. Now, in this case, because we're looking at a two-tailed test, here we have an alpha of 0.05. That means that if I want the total area in these tails to be 5%, then this side would have a 2.5% area, and the right side would also have a 2.5% area. So we're looking for the z-value that has a 2.5% to the left of it and a 2.5% to the right of it. So for this, what we can do is we can scroll back up to the nice table that we had at the beginning of section 8.2. So here we have some common critical values. And what we were looking for is we wanted the z-value that had 2.5% of the area to the right of it. That would be this one. And we see that it's 1.96. So 1.96 is going to be the z-value that lives over to the right that has a right area of 2.5%. So that's 1.96. I'm going to scroll back down and fill that in. Whoops. So what we just saw is that here the z-value would be 1.96. Maybe I'll write z sub 0.025 is equal to 1.96. Now this would be the right one. The left z-score, so the left critical value, you can get by just negating this one. In other words, because these are centered around 0, if this one is 1.96, then this vertical bar over here on the left will be a negative 1.96. So our critical values are plus or minus z sub 0.025, which is plus or minus 1.96. So those are our critical values. And remember that what we're looking for is we're seeing whether our test statistic is more extreme than these, plus or minus 1.96. And what I mean by more extreme is further away from 0. So if our test statistic landed here, let's say it landed at 1, that's not very extreme because our critical values are 1.96 plus or minus. So that would be between those critical values and closer to 0. But if we end up getting a test statistic that's further away than plus or minus 1.96 from 0, then we would reject the null hypothesis. And remember that our test statistic in this case was actually gigantic. It was 12.68. So because this 12.68 is more extreme than our critical values, we would reject the null hypothesis. We can do something similar with the p-value. Remember that with the p-value approach, what we're trying to do, let me maybe draw the picture. I'll just draw it here. So with the p-value approach, what we're trying to do is we're trying to find the area that corresponds to test statistics that are as extreme as ours or more extreme than ours, assuming that we trust the null hypothesis. So if the null hypothesis is true, then this is the shape of the distribution that we should be looking at. But what we got as our test statistic was 12.68. And the probability of getting such an extreme test statistic or something even more extreme would be either this area, or because we're willing to take both tails, this would also be an acceptable extreme value. So the values for your test statistic that are larger than 12.68 or smaller than negative 12.68, both of those would give you more extreme values than the one that we actually got. However, those are pretty unlikely. So what we want to do is we want to compute the value of p, which will be the shaded area here, and it will include both the left side and the right side. Now, because this is a symmetric picture, we can just compute half of p, so p over 2 will be this right area, and then we can double it to get the full area. So p technically means the full area here, both the left side plus the right side area. But in this case, it'll be easier to compute this right side area first, and then we will double it to get the left side area as well. So now what we want is we want to know what area lives to the right of a z-score of 12.68. So for that, we can use our table. Whoops. So I'll go to the table, and I want to be looking up a z-score of 12.68. Now notice that the table stops at 3.4, so a z-score of 12.68 is gigantic. But notice at the bottom of the table here, it says for z values greater than 3.9, just use 0.9999. So remember that that corresponds to this left area over here. So this left area would be 0.9999, and that means that this little right area over here would be 0.0001. So that's the area over here in the far right. So this p over 2 is equal to 0.0001. Now if I wanted the area in both tails, that would give me the full p-value, so I would just double what we just found. So the full p-value would be 0.0002. That would be the area in both of these tails combined. And what this is saying is that there's a 0.02% chance that if the null hypothesis were true, you would get such an extreme z-value. So in other words, only 0.02% of the time would you get such an extreme value if the null hypothesis was actually true. And that leads us to think that the null hypothesis probably isn't true, because we wouldn't get such an extreme value as our z-score if we were really picking from the distribution that was promised by the null hypothesis. So because this is such an unlikely result to get from the null hypothesis, we're going to reject the null hypothesis. So in particular, p is less than or equal to alpha, which was our level of significance. And because p is smaller, we will reject the null hypothesis. Oops. And then if you'd like an interpretation, you can use the percentage interpretation that I gave a second ago, which is that there's only a 0.02% chance that you would get such an extreme z-value if the null hypothesis was true. But if you'd like, you can just sort of abbreviate that and say it is extremely unlikely that we would see such a z-score if h naught were true. So we just took a random sample and we got a z-score of 12.68. That's a z-score relative to that null hypothesis being true. Now, it's extremely unlikely that we would get such an extreme z-score if that null hypothesis were true. Remember that all of these pictures that I'm drawing with these bell curves are sort of assuming that the null hypothesis is true, but what we're getting as our sample mean is something that's way off to the right. And therefore, it's unlikely that we're actually picking from the distribution that's given by the null hypothesis. Instead, it's more likely that the alternative hypothesis holds, that we're not actually looking at this distribution for the speed of leopards. Instead, the distribution is likely something else. So that's how you conclude in these cases. And that's the end of section 8.2 and 8.3. Next time, we'll talk about the last topic that will be on your next exam, which is this proportion z-testing. So there's only one more section. This is